So let me just introduce myself. My name is Titus Koech, in charge of technical support for the Sub-Saharan Africa region. That is support for PV, ESS, and also other components. That is including BAPV. And just to introduce Jinko, that is for the sake of everyone, is that Jinko is basically predominantly a PV module manufacturer since the year 2006, and has been leading globally in terms of PV module shipment and also R&D as well, and also having delivered that is more than 150 gigawatts of PV modules. So just 3 to 5 years ago, we started the energy storage division, where we actually providing energy storage solutions for different segments. That is for residential applications, commercial and industrial applications, and that is basically what we are going to focus on today, and also utility scale solutions as well. So we've had very good success stories, especially in sub-Saharan Africa, when it comes to energy storage solutions. And of course, we started with mostly focusing onto the C&I and residential. And just 2 years ago, we've also launched our utility scale. That is our latest liquid cooled battery energy storage solutions as well, which ideally for today, I'll focus mainly on the C&I, but I will also mention a little bit on the utility as well. So for residential is basically what you call as the sun tank. That is anything less than 50 kilowatt hours. That is having in the batteries. Mostly we have two types of batteries, either the rack mounted, or we can also have in the stackable batteries as well, which is basically our latest generation. There is stackable batteries as well. So that is on the battery side. On the inverter side, we have different solutions. That is between 3 kilowatts all the way to 12 kilowatts as well. So that is only on the battery side. So residential is basically a bit straightforward. That is for the batteries and inverters, and including also the accessories as well. And on the C&I, and ideally this is going to be our main focus for today, is what we call the Sun Giga. That is mostly our containerized solutions. And the good thing is that having discussed also with UDACO, is that UDACO is actually going to have the indoor solutions. That is the complete solution only without the container. And the container can actually be fabricated that is locally, or you can also install in an indoor location as well. So we're going to basically explore more about that today as well. So for these scenarios for the indoor, that is basically what we have between mostly less than 2 megawatt hours and more than 50 kilowatt hours. That is basically our classifications. Though in other scenarios, in some customized scenarios, we can actually get to 6.4 megawatt hours and up to 2 megawatts of PCS. That is for standard solutions. Then for utility, is that ideally this is what we're referring to, solutions more than 2 megawatt hours. Remember, this classification as residential, C&I, and utility is basically our own internal classifications, because sometimes you'll find that C&I, like small scale C&I, is actually less than 2 megawatt, less than 50 kilowatt hours, or even sometimes large scale C&I can be even more than 2 megawatt hours as well. So just to clarify that this is only for our own internal, these all for our own internal classifications. And like I said, we're going to go deep into the C&I energy storage solutions. There is ideally solutions for commercial and industrial, and we have two sets of solutions. There is one is the air-cooled battery containers, which is actually very common. There is the Sun Giga air-cooled battery containers, and usually for this we have this as low voltage. There is less than 1,000 volts systems with PCS ranging between 50 to ideally 500 kilowatts, which can be extended to 1 megawatt by paralleling maybe 2 or 500 kilowatts. Then the battery standard is that we can have standard configurations. We are still going to look into that. That is from 69 kilowatt hours all the way to 1.6 megawatt hours. that is in basically one configuration, which can also be still extended. I will explain how we can also be able to achieve this. And ideally, in our standard configurations, is that we're actually looking at between a maximum of 2 megawatts and 6.4 megawatt hours for these configurations. That is for the standard configurations. If it's non-standard, then we might, of course, evaluate and give a customized solution on that as well. Then the other thing also, I think also is also going to be, we might also be stocking this maybe in after the first batch of batteries is basically the Sun Giga liquid cooled battery containers, which is basically standard battery cabinets. Remember, it's only battery cabinets. There is no PCS, so just standard battery cabinets. We're also going to look into that. That is having capacities of that is 215 kilowatt hours or 344 kilowatt hours. So the difference is basically the number of packs in series. It can either be 5 packs in series to make it 215 kilowatt hours, or 8 packs in series to make it 344 kilowatt hours as well. So, but don't worry. I think just stay along, and we're going to have a deep dive to understand on how we make this configuration, and also what is the difference between the air cooled solution and also the liquid cooled solution as well. So I think that was just to introduce this topic. That is ideally what we're going to talk about today. And now is it for the sec, and also for us to be synchronized, for us to be on the same page is that what is basically BSS. BSS is basically battery energy storage systems. And battery energy storage systems have actually for the last couple of years, let's say 5 or 6 years, you can see there's an increase in awareness and also the need for battery energy storage systems, because one, of course, there is also need to increase the renewable energy fraction, either from PV and either from that is from wind and also other energy sources. So it also goes along that ideally it's easy to integrate, and also it's a bit modular. It's also cheaper compared to other energy storage solutions as well. And ideally also is that what is also motivating battery energy storage systems is louder. I would give a case for South Africa. We've had some few challenges of load shedding for the last couple of months as well. So basically, with the unreliability of the grid, there is basically need for an alternative energy storage. So that is basically battery energy storage is basically one of the most convenient one, because of the cost and also because of the modularity. Because you can see that you can have anything that is even up to less than 50 kilowatt hours and all the way to megawatt hour scale as well. And ideally for the application is that as Jinko, for our BSS solutions, is that we can actually integrate BSS in different aspects. That is from the lowest pattern, that is in an off-grid scenario. Let's say for mini grids and even sometimes for microgrids as well. We can even have in like where we are basically having for C&I mostly, we have in PV plus ESS plus DC generator or grid. That is mostly for hybrid systems. We can also have the configurations for peak shaving as well. So you understand, and also for time use configuration as well. That is basically what is mostly common for commercial and industrial. Then on the other side is that ideally for the Suntel, where we have applications for large scale, mostly coupled to the transmission network for mostly auxiliary services, which is either frequency modulation, voltage regulation as well, and also reactive power support as well. So that is mostly on the utility side. We can also have this on the generation side, and think we're currently working on some utility projects, not in Africa, but in Israel and also in Middle East as well, and also in China. There is hundreds of megawatt hours, mostly for the generation side. Then ideally for C&I is that we're mostly looking at, like I said, mostly peak shaving. peak shaving, of course, including there is ideally demand response. Other scenarios also coupling PV plus ESS and also diesel generators and also grid. For hybrid scenario, there is peak and valley arbitration. Ideally, be able to make sure that we actually charging at night, and or also be able to do what you call demand response as well. There is, of course, there is also configurable with our energy storage solutions. We'll explain how. Then in some other scenarios as well, of course, where you don't have utility grid and you also want to, you basically have diesel generator as the primary source of power, and you do want to do fuel saving as well. So there's also something with coupling with some controllers. You can also be able to do fuel saving as well. So the other thing is that what are we supposed to look at in ideally in this design, in the selection of our battery energy storage system? So there are a number of factors that we're actually looking at. Ideally, if you've been in the energy storage business for the couple of years, is that you'll find that lithium iron phosphate, or rather LFP, is actually more of a predominant solution because of one, there are three main factors. That is one, the energy density compared to other cell chemistries. There is also the aspect of cost as well. There is also the aspect of safety, and also the other aspect of power density as well. And ideally, the aspect of the round trip efficiency as well is also very important. And we've ideally tried to, in our new generation of batteries, is that we've tried in of our BSS systems, is that we actually tried to optimize on the round trip efficiency. I think the maximum now we can do is around 92-93% as well, of course, with our liquid cooling battery energy storage system. Then the other very important fact is ideally for C&I is the switching time that is between off-grid to on-grid. So in most of our PCS systems or the BSS energy storage solutions, we've actually integrated that is either use of thermostats or also what you call static transfer switches to be able to achieve very fast switching times. Ideally, what we've tested in most of our test reports is basically switching time of less than 40 milliseconds. That is between off-grid to on-grid scenarios as well. So this actually comes into play, especially working in manufacturing environments, that you would want to ideally make sure that there is actually seamless switching between off-grid to on-grid scenarios. In some of the scenarios, especially in all scenarios with diesel generators and of course from with an ATS switching between off-grid to on-grid, you will find that the switching time is usually in the S level, that is usually between 1 to 45 seconds, which in some manufacturing levels might actually not be convenient, because it may actually result into stopping of the production. Of course, assuming now, let's say in plastic manufacturing, which is actually very sensitive to power supply and of course the running of the equipment as well. And even some equipment manufacturers usually certify that there should be certain level of power transition between off-grid to on-grid scenarios. In that, when the equipment are running, they're not supposed to have any power outages at any given time. And you'll find that in most of these scenarios is that some customers, or rather some plants, would actually prefer to have basically to have in maybe UPS systems, like rotary UPS systems, to of course to have more of an online UPS to make sure there is no ideally power outage at any given time, which you understand that online UPS is not quite cheap, quite expensive. So we can still, of course, with the MS switching level, we can still, that is ideally less than 40 milliseconds or less than 20 milliseconds, we can still avoid the use of an online UPS. We also need to, of course, to determine that is what is basically the required kilowatt and also the required kilowatt hours. That is the battery capacity and also the PCS capacity. So we are also still going to look into that as well, what we need to look into. Then ideally also the lifetime of the system also. How long do you want the battery system to last, either 5 years, 10 years, 15 years, 20 years. We know now that for lithium iron phosphate, especially for the new generation, you can actually be able to have up to 7,000, 8,000 cycles, which is basically translates to lifetime of up to 20 years. Then also lastly is, of course, also having in the point of connection voltage. So with Jinko is that for our standard solutions, is that for the standard C&I solutions, the output voltage is usually 400 volts. So ideally, you can also be able to still switch or rather step up this to any required voltage, let's say 11, 33 or 66 or even higher than that as well. So you can also determine that as well. So those are just some factors that we basically look into when as a manufacturer, or as a manufacturer, when giving solutions, we look into this scenario, so rather to understand the project so that we can give solution as well. So what you're looking at is that ideally what you're looking at is just to help you understand on what we are providing, and also what Udako is basically going to provide is that we need to understand there is our naming rule. That is, our naming rule is basically JKS. Let me use the first one. That is JKS 69K-50H. So ideally, to mean that JKS is basically a code for Jinko Solar. 69K, that is the rating of the battery in kilowatt hours. Then after the hyphen on the right hand side, there is 50H. That is basically the rating of the inverter in kilowatts. And you see the H is basically to denote that is an hybrid inverter. So hybrid inverter, of course, comes in with the DC-DC converters, ideally for a DC couple system. In other scenarios where we are not supplying, inclusive the DC-DC scenarios, so we usually have it as the P, where you basically to mean an AC coupled scenario. So there is no integration of the DC-DC units. So don't worry, I know if you're a bit confused about what is the DC-DC, what is the PCS and all that, I will still explain in the next few slides. So, and just to show you is that ideally in our standard scenarios where we basically having these containers is that we usually having 3 sets of battery strings. That is 69 kilowatt hours, we have 98 kilowatt hours and 135 kilowatt hours. So what is basically commonly used as standard, that is our standard is basically the 135 kilowatt hours. That is why we have the 135 kilowatt hours, that is as one battery string. Then paralleling to make it 270 kilowatt hours, we can parallel 3 to make it 405 kilowatt hours. Remember, this is only on the battery side. Then we can parallel 4 to make it 540 kilowatt hours. We can parallel 5 to make it 675, all the way to 1.6 megawatt hours. So that is only on the battery side. Then on the PCA side, there is having ranges from 50 kilowatts, 100 kilowatts, 150 kilowatts, 250 kilowatts, and also the 500 kilowatts as well. So that is basically the different ranges. So ideally is in this basically for in our standard product list with the containers. So what we're going to have with Udako in this scenario is just the units without the containers. So the containers can either be fabricated locally or they can also be installed in an indoor room or rather a power room as well. I will still show you a live demonstration of an example of one plant that is 540 kilowatt hours and 500 kilowatts of PCS as well. So how we basically make up the solutions is that, like I said, the core is the battery cell, which is basically lithium iron phosphate. That is lithium iron phosphate battery cell. So you can see we having from the battery cell, then we have the integration. That is the configuration of 2 in parallel and 20 in series to basically make it the battery pack as well. So this battery pack is basically 12.29 kilowatt hours. That is for one battery pack. Then we next is basically to having a series of battery packs, uh, usually either 6, either 8, or also 11. 11 for the 1.5. So 11 by 12.29, that makes it 1.5 kilowatt hours. So you can see 12.29, then we have 11 packs to make it 1.5 kilowatt hours. Then from this 1.5 kilowatt hours, then we now do the paralleling. Either we can do 1.5, we can do 2 to make it 270, 3 to make it 405, 4 to make it 540, and all the way to 1.6 or any required capacity as well. So that is one. Then on the PCS side, like I said, from 50 to 1000 kilowatts or maybe 500 kilowatts, then we can also parallel, that is a maximum of 4 as well. So if we have, let's say, 100 kilowatts, we can parallel 4 of 100 kilowatts to make it 400 kilowatts. If we have 3, we can, if we have, let's say, 250, we can parallel maybe 4 to make it 1 megawatt. If we have 500 kilowatts, we can parallel up to 4 to make it 2 megawatt as well. So, and for the PCS is that we usually have in I will still explain later on in that for the PCS there's a difference between the 50 kilowatts to 150 kilowatts and also the 250 and 500 kilowatts. So for the 50 and 50, 100 and 150, you'll find that it's actually hybrid in that in one PCS cabinet we have of course the DC-AC module, and also we have the DC-DC module that is in one cabinet. For the 250 and 500 kilowatts is that the DC-AC module, or rather the PCS, and also the DC-DC module actually in separate cabinets. So I will still be able to demonstrate to you later on as we proceed. So ideally, also with this is that it can, like I said, these are the two main components. That is the PCS and the batteries. But apart from this, also is that we also have the other accessories, including the cables. That is the cable connections from one battery to the next battery. The other thing that is very important as well on the battery side is that we also have in 3 level BMS. That is the lower level, that is ideally the battery management units. You can see each of the battery packs has battery management units that is basically monitoring up to the cell level. Then also on the rack level is that we also have the second layer of the BMS that is basically housed in the HVU, that is the high voltage box, that is responsible for getting all the data from all the BMUs, and of course sampling all this. Then we can combine now to the third level, which actually goes to the EMS as well, for basically to be able to control charging and also discharging as well. Then the other thing as well is that also to mention is that, like I said, the rated power of the PCS can either be 50 kilowatts, 100 kilowatts, 150, 250, and 500 kilowatts. Then we also have that is the maximum output power, that is continuous power, not for a short period of time, which can actually be up to 110% of its rated capacity. So ideally, for an example, is that for the 100 kilowatts, we can output that is up to 110 kilowatts, that is continuous power. So this is basically the battery modules. So the 69 and 135 kilowatt hours, we've made this as not really standard, but mostly for our some of our standard containerized solutions. Of course, 69 kilowatt hours is actually a total of 6 packs. Then 98 kilowatt hours is a total of 8 packs as well. So you can see the rating of the battery. The rating of the battery pack is actually with 2P and 20S is 12.29. Is usually at 0.5C. Then at 1C is actually at 11.52. So in this scenario is that just to show you on the components of the system, the components of the system is that they mentioned in the previous slide about the two main components that is on the PCS, where we having the power conversion system. The power conversion system, we also, as part of the power conversion system as well, we also have the DC-DC units, which can either be separate for the 250 and 500 kilowatts. Then we also have an isolation transformer. So this is not a power transformer, this is an isolation transformer. So the purpose of the isolation transformer is ideally to, this is where we're getting our neutral. So because this is how we do transition from delta to Y configuration, then transformation from delta to Y configuration, ideally where we get in our neutral, and it also assists in protection against reverse currents as well. Then we also have in the static transfer switch that is either STS or thyristor, which is actually responsible for the seamless switching that I did mention. That is the MS level switching as well. Then in ideally our configuration, like I said, there are two main parts. One is the power conversion system. The other part is basically on the battery, that is on the battery side. So in our standard configuration where we have in the containers, we've actually split the compartments into two. That is the PCA side and the battery side. So on the battery side is that this is where basically we have in one is the battery racks. Number two is we have in the battery packs. We also have in the BMS system as well. We also have in there is the switch gear, there is the DC switch gear as well. There is the isolation switches, which I'm going to show you as well, and all the accessories. And apart from that is that we also have in the auxiliary equipment. That is one is the fire suppression system. The fire suppression system with actually multiple sensors. There is multiple smoke and also temperature sensors as well at different points in the container. We're still going to show you later on about that. Then apart from that is that we also needs to maintain that is optimal cooling in the container. So we also have in the fire the HVAC as well, or rather the cooling system that is also included. So in for the indoor systems is that the fire suppression and the cooling system is basically not included, but we recommend that is actually mandatory to integrate, that is the cooling system, because you understand that when it comes to the warranty for the batteries, we usually give in, let's say 5,000 cycles at 5,000 cycles with certain conditions. Let's say the DOD is 90% and also the operating temperature is actually 25 degrees Celsius. So without the cooling system, and assuming the temperature goes to, let's say 45 or 50 degrees inside the room, or rather inside the compartment where you're having the batteries, then ideally the performance would not be, sometimes even goes beyond below 2000 cycles, which ideally makes the battery not last less than not last more than 5 or not more than 10 years as expected. So ideally the cooling system is mandatory that we recommend. We will talk about the design of the heating load, what you need to basically factor in. We'll give some guideline, but of course it needs to be customized as per the project situation, each project situation. Then also just to mention as well is is with regards to the configuration, especially for the DC coupled solutions. You'll find that, like I did mention, we have the PCS, we also have the DC-DC converters. So the function of the DC-DC converters is basically, it's more of the MPPTs. So each DC-DC is usually rated at 50 kilowatts. So each 50 kilowatts is basically an MPPT, and it usually has in one, there is one input connections. There is a positive and a negative. So, and you understand that mostly according to the same configuration, the voltage range for the DC-DC is usually between 250 to 850 kilowatts. That is to 850 volts, sorry. So 250 to 850 volts. So ideally that translates, assuming now normal 72 cell modules, the 550s or 570s. So ideally that means approximately 18 modules. So 18 modules by 550, that basically means that it's less than the 50 kilowatts. So to be able to achieve this, we need to parallel. We need to parallel the different PV strings, of course, in a combiner box. Then from the combiner box, we'll have in one output, which goes into the DC-DC unit. So, so you can see in this scenario is that in as much as we supply this, like for the small 50 kilowatts hybrid PCS, so it usually has in the PCS and also the DC-DC. I will still show you the picture of how it looks like. But of course, if it's a 50 kilowatt system, then that means one input for the PV. So for you to be able to have in one input for the PV, then ideally means that you need to combine the multiple PV strings, let's say 5 to 8 strings, so that you can be able to connect to the PV can be able to connect to the DC-DC unit as well. So this is not usually supplied as part of the accessories. So just sort of letting you as well to be able to know. Then on the other side as well, assuming a system with only grid, there is only grid. So in the PCS, we usually have in like for 50, 100, and 150 kilowatts, we usually have in four MCCBs. There is 4 breakers, one for PV, one for battery, one for load, and one for an AC inputs. We usually call it the grid ports. So you can see we have PV, we have battery. That is, I'm just trying to create some memory so that you can see that the breakers, one for battery, one for PV, one for load, and one for grid. So for the grid port is that ideally this is where we connect our grid or generator. And in cases where, let's say you have 2 sources, let's say you have generator and grid, then ideally means that you need to have in an ATS. That is, you need to have in an ATS so that you can be able to switch between the 2 sources. Then we'll have one output which goes into the PCS. Then as part of the accessories as well is that we've also provided there is an EMS as well. So the EMS is also included. So the purpose of basically the EMS is to coordinate communication between the different components. That is the PCS, the battery side, and also be able to monitor on the load side and also the grid side as well. And it's also the gateway that is to our online platform, which I will give a demonstration before the end of this session today. So I think maybe I'll pause for maybe 2 minutes. Is there any questions before we proceed?
Thanks, Titus. I have a question.
Yes, please.
The backup or the load support side, that can take the total amount of kilowatts of the PCS, right?
Yeah, it can take, there is up to 110% of the rated capacity.
So when the modules are busy generating, it will export on the grid port, or will it export on the load side if there is AC power?
It will export on. You want to have export to the grid.
So we can export to the grid and to the loads at the same time.
Yeah, you can. No, it usually exports on the load side.
On the grid side or the load side? On the load side.
On the load side.
So the grid side is only an incoming.
Yes, yes, correct.
Okay, so we're not exporting on the grid side.
Yes.
Okay. Thanks, Titus.
Yeah, and also I think you mentioned a very good point as well. Is in some other scenarios where grid export is not allowed, then you can also be able to set to zero exports as well to the grid.
Okay. Thanks, Titus.
Okay.
Sorry, one other thing. We've also got an EMS, right?
Yes, the EMS is also included as well.
How does the EMS integrate with the generator? Is it via the controller, or do we have some other inputs there that the EMS is monitoring?
So from the control for the generator is actually done because the PCS is a bit intelligent. So the control that we currently doing is ideally the start or stop, or basically remote start for the generator, which is basically based on set conditions. One of the conditions that we can set is based on the state of charge of the battery. Let's say you want the generator to start at certain SOC, let's say 20%, then that can be set and it will automatically start. The other condition is also on the peak shaving mode, where you can actually be able to set the starting time on, or rather where you want, at what time you want the generator to be able to charge the batteries. So that can also be set as well. So it will start on there is such conditions, that is to automatically start the generator.
Okay, so but generator, when we talk about generator, it could be grid also, right?
Yes, could be grid as well.
Is there so for diesel generator integration and for diesel saver option, what communication between the generator and the PCS is there in the sense of limiting feedback to the generator? Because the generator will need to obviously always supply a certain amount of power. There is something regulating between, and that's in the PCS, right?
Yeah, so for the
diesel, I mean, sorry, in the EMS.
Yeah, for the fuel saving mode, currently is that we are basically working with third-party controllers, likes of Elum,
Yeah.
likes of Incombi as well. We're actually having there is solutions for fuel saving as well. So it's not something that we do it with our own EMS. So if it has to be fuel saving, then of course we have to use a third-party EMS or other controller.
Okay, I just want to clarify that because it has been maybe highlighted that we can either use in-house, meaning Jinko, or a preferred partner, meaning Elim. So Elim will still need to be used for that, right?
Yes, correct.
Okay. And we can obviously also nominate our own preferred one, right?
Yeah, you can nominate your own preferred one, and because we have that flexibility, because different regions have different requirements, and what we will do is ideally to share. We will share, that is our protocol, our communication protocol, of course, with our addressing register. So with all that is all the information that you can access, so that your controller or EMS manufacturer can be able to know exactly where to get the addresses to get different information for purposes of control.
Okay, that'd be very helpful for the Modbus registers. Thanks, Titus.
Okay. So thank you so much. So that was, and also thank you for the questions. We will still have further explanations in the next few sessions. So the next session that I want to also introduce is something that we're not going to have it in stock now, but later on. But I'll just sort of just mentioning so that we understand the difference, because we're also getting some clients asking, okay, what are the difference? So last year is that we actually launched this liquid cooled bat cabinet. Remember, it's only the bat cabinet, so it's actually a cabinet made up of one batteries, that is the battery packs, so they're quite large, each one being 43 kilowatt hours. So we also have the liquid cooling unit. Ideally, we're not having the normal 8 VSC for purposes of air cooling. We're having this cooling unit. Then we, as part of the battery packs as well, we also having in a cooling plate as well. So we have this cooling plate where we basically have indirect flow of the cooling agent, which is ideally the cooling agent in this case is 50% water and also 50% glycol as well. Then we also have we've also integrated the fire suppression system as well, of course, with a number of sensors. And also we've also add this more of explosion proof design as well. Of course, with explosion proof exhaust fans that is integrated. And like I said before, this slightly bigger battery cell. The previous one that we're using is basically a 3.2 volts by 96H. For this, for the SunGig liquid cooled is actually 3.2 volts by 280H. So you can see it's quite big. That is close to 896 watt hours for each of the battery cells. Then, of course, to be able to make in one pack, we're having a configuration of 1P 48S, that is 48 in series, and one in parallel to make it 43 kilowatt hours. You can see it's quite a very big battery pack. The previous one for the air cooled, we're having 12.29. So, and now we can have in 1, 2, 3, 4, 5 to make it 215 kilowatt hours. That is 43 by 5 to make it 215, or we can also have 1 to 8 to make it 344 kilowatt hours as well. Then you can see is that this design was actually made for our Sunterra, or rather for our liquid cooled, and we decided to make this smaller version for some applications. Mostly we had these applications in China and some parts of Australia as well, and also Europe, of course, with some bit of demand. Then, of course, with this cooling unit, there is actually a cooling ducts as well to be able to ensure that there is indirect flow, or rather direct flow of cooling from the master cooling units to each of the battery pack cooling plates. So ideally, what results to is that the highest temperature point and also the lowest temperature point in these small cabinets is actually less than 2 degrees. So basically, we're able to ensure very good round trip efficiency, ideally up to 94%. Then this is basically to show of what we have. Like I said, we have the different battery packs. We can either be 5 or 8. Of course, with different voltage levels. Then we have a number of alarms, that is the gas detection alarms, the temperature alarms as well, and also the fire suppression system that is integrated in this cabinet. And also we have this cooling system, like I mentioned. Then we have this high voltage box as well, similar to what we had before. So remember, we still have the 3-level of the BMS. That is the lowest level on the battery pack, that is basically the BMU. We have the second level that is on the high voltage box, and the third level basically on the EMS side as well, on the system side, where we can actually integrate to the EMS as well. So with this is that we can actually have in flexibility or paralleling, that is a number of units. What we've now tested is that we can parallel up to around 10 and be able to connect to one PCS. So what determines whether to use 344 or 215 is ideally the voltage level. You can see the voltage range for the 344, because of 8 packs, is more than 1,000. That is to 1,382. So you can see that ideally you would need a PCS which can accommodate, that is this voltage range. Then what is mostly common, especially in the region, is less than 1,000, or rather the DC 1,000 volt systems, that is the 215 kilowatt hours, because of the voltage range, which is ideally around 672 to 864 kilowatt hours as well. So for the fire suppression system is we've had the agents being standard of either aerosol or Novex 1230, but in some other scenarios as well, we can also customize based on the customer's demand, which can also include, that is FM 200 as well in some other scenarios. So that is just to introduce to you about the liquid cooled. I will not dwell so much into this because we want to focus more on that is on the units that is going to be in stock in the next month also. Then ideally, I did mention also about the Sunterra energy storage. So the Sunterra energy storage is mostly applied for large scale utility projects, or even sometimes large scale C&I. That is more than ideally more than 6 megawatt hours, which is our limit for the previous cool solutions. So for this solutions is that we basically have been a standard battery container. It's only a battery container, a standard battery container of 344. 3.44 megawatt hours. So remember, each rack is 344 kilowatt hours. So in the container, in a standard 20-foot container, we're having 10 racks. So 10 racks by 344 kilowatt hours makes it 303.44 megawatt hours in one container. Of course, in some configurations, we can still reduce the number of racks, maybe make it 8, make it 7 sometimes, to reduce the capacity based on the project configuration. So, but the standard is 3.44 megawatt hours. The advantage is that we can be able to parallel unlimited number to achieve that is the required capacity, let's say up to hundreds of megawatt hours as well. And the technology is actually based on what I described for the liquid cool, SunGiga liquid cool before. That is ideally still based on lithium iron phosphate. That is the cell chemistry. The cell that we're using is basically 3.2 volts, 280 Ah. And also we have the other distinct feature about this is that for the SunGiga air-cooled solutions, we can do a maximum of 1C. That is 1C, that is the kilowatts, so kilowatt hour rating being one, that is 1 to 1. Then, but for the Sunterra and also the SunGiga liquid cool, is that we can do, currently we've tested and we can do a maximum of 0.5C. That is the CC rating is basically 0.5C as well. So in the container is that we still have what I mentioned before. That is one is the battery packs with the high voltage box with the BMS as well. There is all the 3 levels, all the 3 levels of the BMS. There is the lower level of the BMU. We have the second level, and also we have the master level as well. That is for the system level as well of the BMS. Then the container is basically IP54. That is ideally designed for outdoor, and it can also, we've also integrated a number of sensors, including gas sensors. We also have temperature sensors as well, and of course we have explosion proof design, because we've integrated this deflagration venting, or other vents as well. Then so this basically the configuration of the Sunterra, of course, with all the packs. Then we have with all the packs, and of course we have the cooling system, we have the protection system for the battery as well, we have the firefighting system that I did mention as well. So these all basically all integrated in one container. So remember, the Sunterra is only the battery. So ideally this means that the PCS is external. is basically external, so it's different compared to the previous air-cooled solutions where we have everything either in one container or in one package. So for this is that we have the battery separate and also the PCS being separate as well. So I'm not sure if there is any questions for the liquid cool. I just thought of mentioning this to you because we might also be sorting this very through DACO in the next year or so. So and also for some projects, large scale projects that is more than, let's say, 6 megawatt hours, we might consider this liquid cool solutions as well. So the thing is that now that we having the indoor solutions, we also need mostly for C&I, and the critical question that we should have in is on the sizing, and of course with battery storage not being a very old technology, we still have some problems, of course, when it comes to sizing, or rather mismatch between the sizing and basically what is provided, and of course sometimes might lead to some bit of either undersizing or oversizing, or basically choosing a wrong product for which is basically not going to meet the requirement of the customers. So ideally, in most scenarios, is that a request that we have in the load profile, which with the load profile, which you can always get it from data logging. Either there is short term, let's say a day or 2 days or 3 days, but what is usually recommended is doing a full week logging of the data, so that you can even a month sometimes, so that you can understand the full pattern of consumption pattern that is, and also the load profile. You can be able to analyze in case of any variations, especially for C&I facilities, let's say a factory. You see the usage actually varies depending on different scenarios. Like now, give a case that the usage during the day might be different with also the usage at night. So it can also be but also be established as well. In some other scenarios also is that the usage between Monday to Friday is also different between Saturday and Sunday, that is during weekends. So that must also be evaluated, so that we have, that is why we usually recommend a full 7 days analysis of the load profile. So I'll give a case just to assume this typical load profile that is from this customer, that is showing in one is the average load and also the peak load as well. You can see is that we basically having more of the day average load between early, that is the start of the day to the end of the day, averaging around let's say 20 kilowatts, around not 20, around 40 kilowatts in this case, around 40 kilowatts. I think the average is around 40 kilowatts. But what you can also see is in a typical scenario is that we also sometimes, if we don't know what is the peak load, it will can lead to making wrong judgment, because if we do our design based on the average load, then we size based on a system that is only, let's say with this, we can say, okay, clearly say, okay, the maximum from this average load, you can see the peak is around 52 or 53 kilowatts, then choosing in an 100 kilowatt system. So, but in real sense, you can see the maximum demand goes beyond goes beyond 250 kilowatts. So ideally, from this peak, we are looking at around 281 kilowatts. So you can see this how this load profile looks like, and also what you can see from this load profile is that ideally the load demand that is during the peak usually occurs, that is during the day, that is between around in the morning hours. So you can clearly see that ideally this looks more of large, of course, with more demand. Maybe the heaters are working in the morning and also at night, that is after 8 p.m. as well. So you can see the rest of the hours is that the load is quite low. So you can see that is basically just trying to understand. But what we're looking at, one is that we want to look into the average load, and also we want to look into the maximum demand, which will actually dictate on the sizing of our PCS. So in this case, is that we just given some bit of summary in that the daily energy demand based on the area from this graph is the daily energy demand is around 829 kilowatt hours. The night consumption is around 525 kilowatt hours. That is from this graph. Then the daily energy consumption, the day energy consumption, that is from 9 a.m. to 4 p.m. That is, we've defined our day to be 9 a.m. to 4 p.m. to be 304 kilowatt hours. So the requirement was basically to provide a solution for this facility. That is a power solution, and also night backup only. Remember, this is basically the customer's requirement. So we are only providing a solution to be able to provide backup at night only. So that is ideally 6 p.m. to 9 a.m. in the morning. So looking at this is that knowing in the daily, that is the daily energy, that is the night consumption and also the day consumption is basically then dividing. Of course, we need to determine so our assumptions in this case is including the safety factor of 25%. We also need to define that is a DC-DC efficiency. In AC couple scenarios, we're looking at the PV inverter efficiency. So we also need to define that as well. We also need to know the PCS efficiency. We also need to know the battery charging efficiency. We also need to know the depth of discharge, what we are working on, 90%, or even when working with the SunTerra or the SunGiga Air Cool, where we can, we've actually determined the depth of discharge at 94.5%. Then we also need to know the peaks and hours, and we also need to know on the days of autonomy as well. So you can see all those factors that we need to factor in. We need to determine, that is our assumptions for the purpose of the calculations. So of course, knowing in that is knowing in the daily that is the daily energy consumption, we can be able to calculate the PV capacity, but of course divided by the peaks and hours and also the efficiency, that is the DC-DC charging efficiency. You can see now this is just basic calculations. That is basic calculations to roughly quickly be able to do the calculations and be able to do your estimation. There's around 307 kilowatt hours. Then, of course, we need to determine as well, there is the PCS capacity as well. There is, of course, we need to know what is the peak load. The sizing of the PCS usually depends on one, the peak load. Then we need to factor in also the safety capacity of it, or rather the safety factor, not capacity. That is, use the IC standard, that is of 25%. So ideally 1.25, then divided by the efficiency, that is ideally in this case the 97%. That is only based on our assumptions. You can see now we basically having around 362 kilowatts of the PCS. Then we also need to size for the batteries. That is also knowing what is basically the night consumption, then divided by the efficiency, charging efficiency, and also the DOD as well. The night load, or rather not night load, but night consumption was 525. And remember, the backup was only for the night. So 525 divided by these two factors to make it 614 kilowatt hours. So this is basically on how to quickly that is quickly basic way to be able to do manual the calculation. Then once you define this, then you can now be able to run in your simulation, either using OMA or using sometimes PVCs to estimate the yield from the PV side as well. Then you can see now there is basically 362 kilowatts for the PCS and 614 kilowatt hours for the battery. Then we're looking at around 307 kilowatt peak for that is for the PV side. Then of course, like I said, in our standard systems, we're looking at standard. We're looking at the battery side. There is two main components. One is the battery side, then the other one is the PCS side as well. So ideally, when looking at the battery side, is that we need to look at what is basically close to 614 kilowatt hours. So if we look into our product list that we mentioned here, there is from standard of 135 kilowatt hours, we can have 270 kilowatt hours, we can have 405 kilowatt hours, we can have 540 kilowatt hours. That is basically 4 battery strings. Then the next level is 675. So 540 is basically less than 614. So the system will be undersized. Then of course it's preferable that we choose that is the second eye level that is basically available, that is close to 614, that is now the 675 kilowatt hours. That is why this. Then for the PCS side, of course, our requirement is 362 kilowatts. So we don't have a 362 kilowatts. So we can choose the next eye level, that is the 500 kilowatt PCS as well. Then on the PV capacity as well, we also need to factor in, let me assume another scenario where, let's say, the required PCS was around 162. So ideally, in this case, we could choose maybe 250 kilowatt for the PCS. But the DC-DC, we also need to make sure that the DC-DC unit is able to accommodate, that is up to 307 kilowatt peak as well. So basically, you need to look into, there is, let me say, 3 main factors. There is one, the battery capacity, so which actually determines on how many racks of batteries you need. Then you also need to determine the PCS capacity, which actually I mentioned from 50 kilowatts, 100 kilowatts, 150, 250, 500 kilowatts. We can parallel up to 4 pieces. Then also you need to factor in also on the DC-DC units as well, that is the DC-DC capacity. Like I said, for the DC-DC, each module is 50 kilowatts. So ideally in this case, 50 kilowatts by 4, 50 kilowatts by 4 makes it 200 kilowatts. It's still insufficient. Then 50 kilowatts by 6 makes it 300 kilowatts. So that is basically more of ideal. Or you can still go with the standard of 50 kilowatts by ideally by 50 kilowatts by 6 to by 8 to make it 400 kilowatts, or 50 kilowatts by 10 to make it 500 kilowatts for the 500 kilowatt system. So, but I will still show you on where the DC-DC are, and also how to identify and how you can be able to reduce the number or increase the number if need be as well.
Titus, just
Yes.
in there quickly, there's a couple of questions in the chat that I just want to quickly address. Emmanuel has been answering them, but I think just for everybody's knowledge, I just want to go through them and just so that you can understand what the guys are asking you. So the first guy is asking
Ian, sorry, I can't. I don't know why I can't see the chat. You know, it's.
Oh, don't stress about it.
Can't...
I'll read them out to you.
Okay. Okay.
Yeah. So one of the questions were, what is the difference between off-grid system and ESS? And I think it's a pretty basic question you can answer quite quickly for us.
So an off-grid system is basically a system that is off the grid. Let me use layman's language, is that off the grid. It's not connected to the grid, let's say in remote areas without grid. An ESS system, an ESS is basically an energy storage system. You see, for an off-grid system, there is so many ways to achieve off-grid. You can use ESS, PV plus ESS. You can even use generators, you can even use hydro, you can use wind to achieve an off-grid system. So for an ESS is basically an energy storage system is a means of storing energy, of which the BSS now is a battery energy storage system, where we're actually using batteries to store energy.
Thank you. Yeah. Thank you, Titus. Then the next one was, what is a water-dry pipe system?
What is?
A water-dry pipe system.
Sorry, I didn't get, rather, I don't understand what you're making reference to. Maybe explain that.
Me also, I thought it was maybe something that was mentioned previously. And so Emmanuel said he thinks it's a sprinkler filled with pressurized air that doesn't allow water to enter it. So I think Emmanuel answered that question quite nicely. The next question is, where's the static transfer switch located on the schematic?
Yeah, the STS. Okay, let me use let me use this. So you can see I'm just using this scenario where we have in I'm actually using this. Is actually part of it's on the grid side. Is on the grid side of the PCS. So the STS, you can see this is the PCS, right? So we have the grid. So it's usually on the grid side of the PCS.
Fantastic. I would like to ask one more question. Here's this one now. I think I've lost it. Oh, that's it. I see. Oh, sorry. I'm gonna call you our son. I see your hand is raised. Would you like us to unmute your mic? I'm gonna allow you to use your mic. Please unmute yourself and feel free to ask the question. Hassan, we've unmuted your mic. Otherwise, what we can do is please pop it into the chat. We'll read it out for you. Okay, thanks, Titus. You can continue on.
Okay, thank you so much for that. So the other thing also is, was what we also noticed, of course, most of the customers have actually been working with AC coupled systems, of course, with PV inverters, of course, with MPPT voltage ranges that is well stipulated, with usually around between maybe 250, sometimes 150, depends on the PV inverter, to maybe 1,000 or sometimes 1,500 as well. So for the DC-DC as well, we've also, like I did mention before, we've also given the ranges of the voltages. There is the ranges of the voltages. But what we also need to know is that for DC coupled systems, this is actually a very important point, is for DC coupled systems, we need to pay into attention with regards to the battery voltage range and also the PV voltage range as well. Remember, the battery and the battery and the DC, the battery and the PV actually connected in the same more of the same bus bar. So and the DC-DC can work in they actually buck boost converters, so they can work in different modes. That is one, it can work in the back mode. Number two, it can also work in the boost mode as well. So let me explain. What do you mean by the back mode? The back mode is basically scenarios where the PV voltage is actually more than the battery voltage. So ideally, what it means is that the DC-DC is actually stepping down the PV voltage from higher voltage to a lower voltage to be able to charge in the batteries. Then on the boost mode, we usually have configuration where the PV voltage is lower than the battery voltage. So ideally, the DC-DC will have to, in another way, let me say, step up the voltage. It's still DC voltage, but step up the voltage to higher level to be able to charge in the batteries. So that is basically the two configurations. So if you need to follow this. Is that that is why we have this PV modules configuration guideline, which we've actually given. You can see now for the 69 kilowatt hour battery systems with only 6 batteries, so we can have in that is ideally lower voltage range, that is between that is up to 396 kilowatt hours. For the 135 kilowatt hours, the rated voltage range, we're actually looking at around rated voltage of around 704 kilowatt hours. For the 196, you can see around 512 kilowatt hours. For the let's say for the 405, it's still 704 because it's still 3 batteries in parallel. So you can see still at the same level. For the 675 as well, it's still 704. For the 1080, that is basically 8 batteries in 8 battery racks in parallel, it's 704, 704. So we, and at any given time, we've also given the guideline of what is, of course, for the 105 kilowatt hour systems, we usually have these configurations on the boost mode, on the back mode, sorry. So ideally for the back mode is the voltage of the PV side must always be more than the battery side by more than ideally 50 volts. That is the difference between the PV voltage and the battery voltage, usually more than 50 volts. So that is why we've given configurations that, let's say for the 1080 500 kilowatts, you can see that we've given the guideline that the voltage must be between 756 to 950, 756 to 950. That is using the 105 kilowatt hour battery strengths. For the other battery strengths, we've also given ranges between 426 to 950, 756 to 950. We've also given 558 to 950 as well for the 98 kilowatt hour battery strengths as well. So we need to pay into attention to this, because if let's say you have lower, let's say lower PV voltage compared to the battery voltage in the back mode, then you'll find that there is actually limited, the batteries will stop charging. So you need to pay into attention into this, that the PV voltage in the back mode must always be more than the battery voltage by at least 50 volts. And the good thing is that we've given this guideline. I think this will be shared by everyone who joined today. And of course, we've also given a guideline on how you can actually use in our standard modules or any other modules to be able to calculate. That is using the temperature coefficient to be able to calculate on that is factoring the temperature coefficient to be able to calculate on the actual voltages on site, so that you can actually determine on how many modules you require to have in how many modules you require to have in one string, of course, to achieve the required voltage. So I'm not sure if there is any question on this point.
Titus, I do have one question here in the comments. When there is a fault on modules or cells, is it possible to change the single module or single cell? The OEM is on a module or track or rack level. Do you understand that question?
Yeah, for now is that what we, yeah, I understand what he's saying, is that can we repair that is up to cell level. So the thing is that we can from our monitoring system, that is our battery monitoring system, we can be able to identify a defective cell. So for now is that what we're focusing on is replacing the pack. Then as we work with Udako as well to establish our service center, then we will be repairing that is up to cell level, or rather replacing the cells as well, because it's something that in the battery side, and in the battery side we have or rather in the third level EMS, we basically having an HMI screen which can also be able to show us that is data up to be able to identify on a defective or rather a malfunction cell, so we can still replace. But at the moment, the replacement is on the back level.
Fantastic.
Okay.
Titus, I have a few questions here.
Okay.
If we do go over amperage, what will happen? Is it just clipping, or will it be worse than that?
If you do, sorry?
If we go on the over amperage on the string sizes, is it just clipping that will happen?
Over the rated.
Yeah, over the rated input current on the strings.
Yeah, of
What
course.
will happen?
Yeah, that is now going past the upper limit. That is having a risk that it can even damage the electronic equipment in the DC-DC modules.
Okay, so it's crucial to stay under the amperage.
Yes.
There's no protection. The system will not automatically clip the amperage by itself.
Yes, correct.
Okay. Thanks, Titus.
Titus, I have a question that came through here from Alan. He asked, what type of fire suppression system would you recommend? So this could follow up in two. So there's a part one from one person, and there's a part two from Hassan. And part one is, what type of fire suppression system would you recommend? And then part two of that will be, LFP batteries can catch fire. And if used in a clothing factory, then the fire can spread easily. Other than built-in cabinet fire hydrant protection, what precautions can be taken? And is there any LFP certificates for anti-fire hazards?
Okay, so for the fire protection is that what we mostly use, especially for most of our units, is either FM 200. We can also use Novec 1230 as well, but you can also use aerosols as well. So that is one. So and also what you can do, I think also Daniel and James and Ian as well, will also share that is the details of our current fire suppression system. So I think we can also share this with everyone so that they actually know exactly what we are using for that is for our current battery containers, so that they can check in for maybe an alternative that is available locally. Then the other thing is that, of course, the thing about fire protection is that it needs to be quite robust, and of course you need to have in multiple sensors. That is why in our case we usually have in the temperature sensors and the temperature sensors and also the smoke sensors, which can actually be able to, it's more of creating redundancy at different levels as well. So that is number one. Of course, having multiple sensors in either the power room or either the container as well, that needs to be factored in. Then the other aspect is, I think it's also ideal in some other scenarios to be able to separate or rather to have different compartments for the PCS. It might not be practical in some scenarios, but having different compartments for the PCS and also the battery side as well. So that can also be one. Then the other thing also is just one we need to follow, that is local regulations. That is number one. It needs to be local, because in as much as we have our own standards as Jinko, it needs also to follow local regulations. Then number two is that we also need to we also need to do proper electrical designs, especially with cable sizing. It's very important, because we just I just did some personal research on what is basically the cost of the previous fire incidences that occurred, maybe not in Africa but other regions. Was mostly one either because of thermal runaway or also cable undersizing as well, which of course leads to overheating of the cables, and of course fire that is spreading into the system. So ideally we need to make sure that the cable design is actually optimal. We need to factor in the safety factors and all that, make sure that we're choosing the right cables as well. That is everything. That is ideally following the standard electrical design and also the local regulations. Then I think it won't we won't have instances of maybe fire hazards as well. And also to mention one thing as well, for the Sunterra and Sun Giga, is that the advantage is that you see with this with the cooling plates that we've implemented, we've actually added in what we call mica sheets. Mica sheets will actually avoid that is between one pack to the next pack, so it will actually avoid thermal runaway from, let's say there is a fault in one of the packs, so it will actually avoid the thermal runaway from one pack to the next pack as well. So for the new SunGiga SunTerra liquid cool solutions, we've given multiple protection levels against fire.
That's fantastic, Titus. Thank you so much. Then James Shirley, our MD at Udaka Energy, also commented and said, we own a fire suppression company, so we can get hold of the local equivalent as soon as we receive your document and can make the solution available alongside the balance of the indoor BESS components. So within the Udaka group, we have a fire suppression company, which we'll source in for you and will assist you with anything that you need from that point of view.
Okay. Yeah, I think that would be part of just having in a very experienced fire suppression company will solve most of the problems.
Exactly. So I have another question here. Is SunTerra always 3.44 megawatt hours as standard, or is it scalable to lower capacity, such as 3.2 to 3 megawatt hour range by excluding the racks inside?
Yeah, so like I said, the SunTerra 3.44 megawatt hours is actually made up of 344 kilowatt hours. Remember, I did mention that it's made up of 10 racks of 344 kilowatt hours. So let me explain here. So this is one 3.4. This is basically 344 kilowatt hours. So if you want to, let's say, having 2 megawatt hours, or you want to have in, let's say, 2 megawatt hours, then you can, let's say, have 8 units of this. So 8 by 344 kilowatt hours. So it's not now SunTerra, but the SunGiga, the C&I version, the SunGiga that is liquid cooled. So 344 kilowatt hours, then you can have in maybe 8 units in parallel to have in that capacity. So it's 3.44 by 8. Or of course, remember the voltage level is 1000 to 1382. So if you want a lower voltage level, let's say less than 1000, then we can have the 215 kilowatt hours. So 215 kilowatt hours by 10 units, 215 kilowatt hours by 10 units makes it 2150, or rather 2.15 megawatt hours. So if you want lower capacity, but in other scenarios, the 3.44 megawatt hours is this in the container now is standard. So, but remember, we have 10 racks, so we can still, in some other scenarios, let's say we want to parallel 2 containers with a total of around, let's say, 5 megawatt hours. So we would want maybe to reduce the capacity in one container. So we can still remove, let's say, 2 racks to make it 8 instead of 10. That is in one container. But if you want the more of the cabinets, the outdoor solutions, only the racks, then you can have in these units.
That's amazing. Thank you, Titus. Anybody else?
Thanks, Daniel. Titus, just coming back to the design with the input on the PV versus battery voltage. Do you recommend we use STC or NOCT values of the module to design our strings?
I think it's usually required to use STC, but of course with temperature correction.
Yes.
Yeah.
Okay.
Of course. Yeah, with temperature correction. Yeah.
Coefficients. Thanks.
Yes. Yes.
Okay. Thanks so much.
Yeah, but don't worry, because I think Ian, I think we've sent this document to you. You can share with everyone. and also still reshare as well. You can still share with everyone for better understanding.
Excellent, Titus. Also, the warranty process. Thanks.
Okay. Yeah, sure. And that is very important. I think I'm still going to mention about that as well.
Okay, cool. Thanks.
Yeah. Any more questions before we move into just about the installation? Just quickly about installation, what we need to do.
Mr. Titus, I think the one question we missed, what is the auxiliary system consumption value in full operation mode? I think this refers to the Sun Giga liquid cooling system. What is the total energy consumption on that?
That is for the Sun Giga or the Sun Terra?
The question is for the consumption on both Sun Giga and Sun Terra.
Okay, so we will share this information because it's usually specific with number of packs. So we'll share this information also for the Sun Terra as well. Because you can see now for the Sun Terra, we actually just mentioned on only 40 kilowatts. That is the maximum cooling capacity. But we will share more information about the cooling, that is the cooling capacity for each of the solutions.
Perfect.
Okay. So I will quickly, I think we still have close to 25 minutes. So I'll quickly move into the installation bit on how ideally we need to address on how complex is the installation. So it's not really complex, it's a bit straightforward, but of course we need to first understand on basically the installation steps. So, and with discussion from Udako, James, and the team as well, is that once the units arrive, I think we'll organize for another physical session as well to be able to do a live demonstration on how to do the installation. But of course, for the installation, one thing that we need to pay into attention is basically the installation site condition. And ideally, one is that for the indoor units, one thing that we need to pay into attention is the installation room. That is, we need to make sure there is proper cooling. Of course, that is well integrated, and we can also integrate this to our EMS as well. We also need to make sure that there is all the safety measures, of course, exit doors and all that. There is also some bit of venting as well that we need to pay into attention as well. There is a proper warning sign as well. Then we basically need to do there is proper planning of the equipment on where we need to place in our equipment, where we need to place in the batteries, where we need to place in the PCS as well, the DCTC, and the EMS, all the control equipment. Also the cabling, how to manage the cabling as well. Then we also need to make sure that in scenarios that we're looking at, we also need to make sure that there is also anti-flooding protection as well. That is very important for construction of power rooms. So you need to make sure that there is proper measures in that there is no instance that we can actually have in water in the containers at any given time. So if we have that, then I think that will really help us. Then for the equipment is that one is that look at this building layout. Is that where we have in the batteries, and we also need to have in we also need to have in the PCS as well. We also need to have in the DC cabinet. The DC cabinet is basically where we have in the DC breakers. There is the DC breakers where we're running the cables from each of the battery racks as well to from one rack to that is to the DC switch. Of course, from the DC switch to now the PCS as well. So we need to basically have in planning for that as well. So what we need to pay into attention is ideally it's actually desirable that the cables between that is ideally from the DC cabinets to each of the each of the battery each of the battery racks must actually be equal. They must actually be the same length of cables. That is one thing that we need to pay into attention as well. So ideally, it will determine on how we do the planning of that is the planning of our that is our building. And of course, you can see now in this scenario is that of course with more classes, desirable to having the batteries, some of the batteries on this side, some of the other batteries on this side as well. Then we can have uniform cable distance, that is from the DC confluence cabinets to each of the battery racks. Then also on the right hand side as well. So we need to be able to make sure, but you can still share more guidelines on this. Of course, it depends on the number of clusters that you're going to have in. Then of course, the main components that we're having in this system is basically the battery racks, that is the 1.5 kilowatt hour battery racks. Then we also have in the PCS as well. We also have the confluence cabinet, that is basically more of the DC combiner box with different switches. We also have the fire suppression system as well, that also must be integrated as well. We have the DC-DC converters as well, where we have in the connection of the PV modules. Then of course, the cable inlets on either the PCS or the DC-DC and also for the battery side is usually from the bottom side. So you also need to give provisions as well. Of course, when planning for your foundation or for your plinth, you also need to have in, that is the cable ducts, rather to planning for that is bottom access, or rather bottom access, where you can basically have in the cable inlets and also the cable outlets as well. Then on the cooling side is that, like I said, the cooling is you can reach out to DACO when you want to design the cooling. Of course, the cooling for our containerized solution is more of standard, because we've already done in the cooling or rather the heat load calculation. But for the indoor units, I think it also needs to be site specific. That is, you need to assess the site, that is the power room that you're going to have in the batteries, and be able to calculate the heat load. But we've given this guideline on basically what is the heat load capacity for the PCS. For the 50 kilowatts, you're looking at around 2.75, 100 kilowatts around 4.9, all the way to 500 kilowatts around 32.5. Then each of the battery strengths, especially when working with that is standard C rate of 0.5 series, we're looking at around 1.6 for the batteries. That is for one cluster of batteries. So if you're looking at around 10 clusters, so that means 1.76 by 10, 1.76 by 10, that makes it 17.6 kilowatt hours. That is kilowatts, sorry. Then also for the C rating, because 1C, that is for 1C batteries, of course, in 1C configuration, let's say 500 kilowatts and 500 kilowatt hours, we need to give that is around 4.4 kilowatts for each of the battery racks. That is ideally the 1.5 kilowatt hours. So if you're looking at 10, so that makes it around 44 kilowatt as well. So you need to basically make in the configuration, or rather the consideration for that as well. So we've only given this as a guideline. Of course, the cooling needs to be specific to, of course, the region and also the site conditions as well. Then on the components, is that for us to just understand is that we have let me say on the we have two main components. There is one, the batteries, where we have clusters of batteries. You can see from this picture we're having two clusters of batteries. So you can see from battery number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 batteries. Then of course we're having all the terminations. That is, the series connection is actually terminated on the high voltage box. So the high voltage box, we basically have in the DC breaker, and also we have in the second level of the BMS as well. Then each of the batteries will basically have in as that is a battery management unit, that is the BMU. Then of course we'll provide all this. Then there is also, of course, the paralleling cables, not paralleling, but the battery cables that we use for the DC, that is for connection between battery number 1 to battery number 11 as well. So that it is also provided and well labeled. So series connection from battery number 1 to battery number 11. Then we also have in the communication cables, of course, for the BMS. That is communication cables. There are 2 sets of communication cables for the BMS and also for the fans. So 2 sets of communication cables from battery number 1 all the way to battery number 11 as well. So all series connection. Then this basically terminated on the high voltage box. So this is the high voltage box. You can see B positive, B negative. That is the battery. From the inputs, positive from the battery, and input negative from the battery as well. Then we also provided, of course, we have this P positive that is to the PCS, and also the negative cable also to the PCS as well. So this is only for the, like I said, for the COM cables and also the fan power cables as well. This is also on this. Then for the
Titus,
yeah,
sorry, James
yeah.
here.
Yes,
I'd just like to point out, thanks very much. For the first 10 systems, in other words, for the first order that's coming now, we have included in our cost the pre-terminated comms and cables from the battery to the HV controller and from the HV controller to the inverter. So the DC power cables and the comms cables are included in the first 10 systems that are going to be ordered. Those are already pre-terminated and cut to equal lengths, so as to not deal with any issues based on cabling side for the first installers.
Okay, thank you so much.
That's just for everybody on the.
Okay, so because the thing is that the reason why we're actually working with DACO is that we're trying also to see, of course, for the first few systems, we are going to supply including all the cables, but for the next few systems, we'll have been DACO supply this locally. So we're actually having some high-level discussions to agree on this. That is to agree on the standards. That is our standard. So the first systems is just provided for guidance. Then, of course, we also have the conference cabinet, or of course the DC cabinet, where we're having all the terminations for the DC. Of course, for the DC from the battery side, where we're having in all the terminations, and also we have the breakers as well, and that is the DC switches as well. We also have this the UPS. That is UPS. That is, we also provided the UPS as well. Then we also have this HMI. That is around. It's actually a 10-inch HMI, of course, which is actually collecting data on that is on the DC side, or rather than the battery side. That is from the 3rd level BMS. So all the battery data will be from this particular screen. That is all the battery data to be able to check to monitor up to cell level. So you can always get it from this point. So if you want to monitor and be able to determine exactly if there is a defective battery cell, then you can always be able to check from this HMI. Then on the other side as well, we also have the PCS. The PCS also is actually standalone, and it also comes in with 7-inch HMI screen as well, where you can be able to monitor. That is, you can also be able to make settings, to make changes in settings, the configuration of the PCS, the working mode, the different configuration, the different set points. Then you can be able to make it from the PCS side. Then you can also on the back side, I'm still going to show you, is that you can also be able to do that is, you also have in the dry contacts, like now for starting off the diesel generators, and also getting to know the grid situation as well, to be able to initiate that is the grid charging as well. So that is also, we also have in the dry contacts. I'm still going to show you in the next slide. Then like I said, in the 50 kilowatts, 100 and 150 for the PCS, we have the DC-DC included inside. For the 250 and 500 kilowatts is actually separate. is actually separate. So to just explain to you what I'm actually referring to, this is basically the 100 kilowatt. This is actually the 100 kilowatt system. So you can see the PCS on this part. You can see the breakers. That is the battery, the PV breakers. We have the battery breaker, the grid breaker, the bypass maintenance switch as well, or rather breaker as well. This is basically included in. Then we have the modules of the DC-DC. You can see we have 50 kilowatts and 50 kilowatts to make it 100 kilowatts, which we can also still expand to 200 kilowatts. So you can see we can still add in 2 modules. You can see 1, 2, so we can make it 50 kilowatts by 4 to make it 200 kilowatts as well. Then on the PCS, of course, with all the auxiliary breakers, you can see also this for the 250. So this is basically the DC-DC cabinet. That is the standalone DC-DC cabinet. Remember, for this, we having one PCS, and inside the PCS we having the compartment for the DC-DC. For the bigger units, we have separate modules or other cabinets for the DC-DC. That is 50, 50, 50. We can expand to 6. So 50, 1, 2, 3, 4, 5. That makes it 250. Which can be expanded. You can also add in 1 module to make it that is 300 kilowatts. That is for 1 cabinet. For the 500 kilowatts, we have 2 cabinets. So 1, 2, 3, 4, 5, 2 cabinets to make it 500 kilowatts. Then we need to DC chain that is between the 2 cabinets. Then this is basically the system controller that is responsible for online monitoring as well. Of course, with a SIM card slot, you can also be able to configure that is for Ethernet as well. There is wired cables, wired internet as well. So this can also be configured too, or you can use, there is a normal SIM card that is open to any network. So any SIM card you can use. So, and of course, like I said, this is the backside of the HMI that I showed in the previous screen for the PCS HMI. So for this, you can see that we have a number of contacts which we can use, either normally open or normally closed contacts, which you can use to be able to control that is starting of the generators and also the grid as well. So that is also possible. And also we can also be able to that is using RS-485 to also be communicate to external, that is with external EMS or external controllers as well. So that is possible. So all these components will be supplied, and I think in the next month or so we are going to have them in stock for purposes of demonstrations and further training as well. So I just prepared this to show you. This is one of the projects that we've implemented with Indo. Today, I'm actually not going to show you so much of the containerized. We've done so many in the region, but I'm just showing you this demonstration for the Indo units, where we have in the batteries on this side. You can see the plant, and also we have in the PCS on this side as well. This is basically a solution that was 500 kilowatts by 250 kilowatts by 540 kilowatt hours. That is 250 by 540 kilowatt hours, mostly used for backup. So there is no DC-DC. So you can see the batteries on one end. That is the different racks from bank number 1, 2, 3, 4 to make it 135 by 4. That is 540 kilowatt hours with all the batteries, all the connections made. Then we also have in the PCS on this side. Then we have the DC conference cabinet, of course, with the BMS and the screen that I did mention. Then, of course, this is basically only on the AC combiner box as well, or rather the AC combiner box. Then they provided the cooling system, of course, with these fans, and of course, the one of the air conditioning units as well. So I just want to show you briefly a video. I just ran through to show how from the battery side. This is the high voltage unit. This is the high voltage unit that I mentioned to you. This is the BMS, the battery pack, then the BMS, of course, with 2 fans. The black cables, actually the connection cables, and then goes to this basically now the PCS. the dimension to you. We have, you can see we have 4 switches for 4 batteries. The screen as well. This 1, 2, 3, 4, each for each battery cluster. This is the UPS, of course, for providing auxiliary power to auxiliary equipment, including the screen as well. So this is the screen for the BMS. Then this is the PCS on one end. You can see the auxiliary switches as well. 250 kilowatts, like a dimension. Yeah, the SPTs for the DC side and also the AC side that is provided. Then the switches for the battery, for the load, and also for the grid as well. And yeah, this is the system controller. System controller goes with SIM card inserted. Yeah, then this is basically now the screen to show the power flow. You can log in, we'll provide the passwords to be able to make configurations. Can be able to make configuration, the different configurations. This is actually stipulated in the manual. You can always make reference to. Yeah, so don't worry, because we have a full video, which I think we'll be able to share as well. It's quite lengthy. So we'll be able to show you on how to do the different configurations, simplified installation manual in video form. So this is basically the switching process. I don't have to go into this. I think we will do this when we're doing practical, that is step-by-step switching as well. So I don't have to go through really into that as well. So maybe just to get back to you, I know we've asked so many questions. Are there any other questions as well?
Titus, we have a couple of questions at the moment. So there was one from Zander. He asked, can you add battery packs as an upgrade to existing system?
Maybe you can open the mic so that you can explain on adding battery packs to which, because our strings is actually 1.5 kilowatt hours. So 1.5 kilowatt hours. So we cannot add, let's say, more than that, because we also need to pay into attention the voltage ranges as well. So I'm not sure on adding, because our design is basically to expand from one rack to the next rack, not expanding on the on the rack level. We need to parallel the rack. Maybe you can explain.
Titus, sorry, I think the question is more around if you have, say, a 405 and the client suddenly comes back 2 months later and says, look, I need a little bit more. Could you upgrade to the 540 or 875 or whatever it is?
Yeah, we can upgrade, but we also need to upgrade on, let's say, from the 69 kilowatt hours, upgrading to 135 kilowatt hours. One thing that we need to start with is we need to start from upgrading the rack. That is the rack to be able to accommodate. There is more batteries. Then number 2 is, of course, we need to have in the cables as well to be able to parallel the batteries, the battery packs. The number 3 also is that we also need to reconfigure the BMS as well.
Okay, so to summarize, I think for South Africa, we're not really going to be bringing in the 69 kilowatt hours from Hudeco's side, unless it's for a specific project or a specific client. But it's not an item we're going to stock, because the residential systems are getting larger and larger and sort of encroaching on that space. So certainly for us, we will be keeping stock of the 135 kilowatt hour racks. Obviously, initially we have to build up that stock, but so we would keep them at 135. So as I understand, then the comment is you can add them later on. So maybe, I don't know, 6 months or a year, whatever, after the original one. But the high voltage connection cabinet has to have enough inputs. In other words, to go from 4 to 5, you would have to replace the high voltage input cabinet to one with 8 inputs. The cable lengths would have to be identical, and all the battery racks would have to be at 135 kilowatt hours. We couldn't mix and match sizes. from a hardware perspective, and then finally we would have to go in after the installation of the additional batteries is done, and we would have to reprogram the BMS. Is that correct?
Yeah, correct. You're very right. Thank you, James.
Okay, thank you.
Yeah, so I also want to, I think I did promise as well. I'm hoping you can see my screen, because it's also good for us to, like I said, we are providing our, there is our monitoring platform as well. So just to walk you through, is that because once we provide this platform, you can be able to monitor, that is the performance of your plants. That is, you can be able to get in data that is also in Excel format as well. You can also be able to generate reports. You can also be able to basically check in alarms as well. You can be able to see that is on the left side where we actually checking on what is the target generation, what is the actual generation, be able to compare this as well. You can see the real-time power of the PV, the load, the battery as well, if there is grid as well. Then you can also be able to check in that is the component real-time data. Of course, like now for these plants, we have five different it's MPPTs, that is 250 kilowatts. You can be able to check on the different data as well. You can also be able to export this to Excel, that is 1 to let's say to 5. You can also be able to check in the total power of the PV modules as well, the total current as well. So you can be able to check that on the battery side as well. You can also be able to check in exactly what is basically happening. That is from cluster number 1 to cluster number 8. Like for now, for this case, is that they've actually disconnected cluster number 6 because there was breakage of one of the communication cables as well. So that is basically what we're trying to replace right now. So you can be able to check in exactly what is happening. So these are what you can check remotely. This is what you can be able to check in remotely. So the different data, and if everything is normal, if it's not normal, then you can be able to check in, and also the occurrence time. Then this will also be able to show you on the PCS side as well. You can also be able to check in the data. That is the voltages. Like now you can see this case, the voltages. You can see this the voltages inside the inverter. That is before the isolation transformer is around 270. That is the voltage is 270. That is the line voltages between 270. But after the isolation transformer, the line voltages is now 400. That is 400 volts. Is basically selected to work with that. Then you can also be able to check in the air conditions. I think they're currently offline. I think there's the communication is not. We have 4 air conditioners, so we can be on the status of each of the air conditioners, be able to show you that is the operating conditions. Then you can also be able to check in the data, that is either DLA real-time power data for the PV. I think it's a bit slow. My network is a bit slow. You can also be able to check in the daily yield as well. Check if you can load in a bit faster. So we can be able to get in the data, of course, for purposes of your reporting. So one is that you can check the yield for the specific date. Let's say you want to pardon my internet here. So yeah, this is basically today. You can see the generation was maximum around 47 kilowatts. Then you can now go to a specific day. Let's say you go to what happened yesterday. You can select a specific day, let's say this date, and be able to monitor on what is basically the generation from the plant, from the PV side. You can also be able to check in monthly yield as well. It will show you this plant was just installed last month. You can also be able to check in the yearly yield, let's say for a plant that has been, that is for the whole year as well. Let's say for the next year, we'll be able to check in 2023, 2024 as well. Then dissect data as well. Then you can also be able to check in remotely. That is different loggers that is included for the MPPT controllers as well, the performance for the BMS as well. You can also be able to check in and also be able to configure. You can actually be able to change some bit of settings. We don't give access currently, but we're looking at it because some customers a bit they can change in some of the settings, which is quite difficult to troubleshoot and be able to rectify if you make wrong changes in the settings. So this is also possible in that you can change in there is some of the settings remotely. Then the plant event is basically to be able to check in some faults. Let's say there is some alarms that actually occurred in the plants, that is during the day or yesterday. Like today, there is no alarms. There is no alarms for the day. But if there is any alarms, then it will actually be able to show you, so that you know exactly what has happened, and can also be able to troubleshoot as well. Plant is in Mozambique and all this. Then the analysis is basically to check in on the data, the performance of the data, the low voltage side, the high voltage side. Then the high voltage side is basically on the PV side, low voltage is on the battery side. It will show you the different components, if they're actually working correctly or not. Then you can compare also the performance. Like right now we have the 5 MPPs, so you can actually be able to compare the performance of the 5 MPPs that is for the day. So you can be able to have this analysis. Then once you do this, that you can actually copy this picture and have this as input to your report. Especially when you're doing a report, you need to do your PPT as well. Then we also have in the real-time that is basically showing on the real-time performance of the data, the battery state of charge, the load, what is the load capacity. Like right now the load is around 9.6. You can also see the PV as well at this given time. Then you can also see if there is any grid as well. You can see the voltages, the load currents as well. That is all this. So with this is that you can actually be able to monitor real time with regards to the performance of the plant. Then this platform is basically free of charge. You don't need to pay for that. Then you can also be able to change passwords. You can also be able to create new users as well. Let's say you want to create access level for, let's say you want to create an access level for the customer. You can also be able to create as well. You can also be able to define, that is role management. You can also be able to set in as well. Let's say you want to have in, let's say someone to get, let's say, alarms for warnings or fault in a certain power plants. Then you can also be able to configure this from this point. So this is also one of the flexibilities for our that is our monitoring platforms, to be able to give it to the customers. Some customers would want, maybe like I think someone mentioned that they have in their own platform. Then that is also possible as well. But you can still have in this platform that is not paid for. There is no tickets that you need to pay for that. Once you bought in our system with the controller, then you can have access to this monitoring platform. So I think that is the end of my presentations. Is there any more questions?
Titus, I think we've answered all the questions. Thank you, Emmanuel, for answering the questions on the chat so far. We thank you. We don't want to take up too much of your time. We thank all of the viewers that came through today. We thank the presenters from Jinko's team and the internal team from Adeka Energy. We will be sending out the emailer later on this week with the recording to this session, as well as the PDF of the presentation to anybody that's interested and would like to forward it on. Our first systems of the Jinko indoor solutions will be arriving in the 1st of October towards the end of September. So please be sure to speak to your sales representative, and they'll be able to assist you with any costings that you might require from our side. Thank you so much, team, and have a good day.